Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next lecture. Before we do that, let us quickly recapitulate what we learned in some of the previous lectures. You might recall we were discussing about the various mathematical operations that can be performed using an operational amplifier. There are several applications like multiplication by a constant, summing amplifier, difference amplifier, integration amplifier, etc. In the last lecture, you might recall we discussed about a difference amplifier and also how we can sum on both inputs, the inverting and the non-inverting inputs, and we also tried some simple problems as an illustration, and then we discussed in detail about an integrating amplifier using operational amplifier. Now this lecture we will try to look at the next mathematical operation, namely differential amplifier. So I just want to show you a couple of slides which we have seen already in some of the previous lectures about the various mathematical operations that can be performed using an operational amplifier. Like for example, on the screen you can see multiplication by a constant, where the output is some constant multiplication of the input, then a summing amplifier where the output is the sum of the two inputs with a constant factor if you want, and then difference amplifier where the output voltage is proportional to the difference in the two input voltages. Then we also saw integration being performed where the output voltage is a time integral of the input voltage V in dt. V output is equal to k times integral V in dt. We saw some examples of this, we also saw a demonstration. Today we will discuss on the differentiation circuit, where output voltage is going to be some constant multiplied by the time derivative of the input voltage dV in by dt. V output is equal to k times dV in by dt. How do we do that? So to understand that, you can recall some of the earlier circuits that we have already saw. One of them is just a simple network with one capacitor and a resistor in series connected to a signal source V in. This we called by different names earlier. For example, this was called as a lead network when we discussed about the frequency response of RC coupled amplifiers. You might recall we discussed in detail about the behavior of this simple network which involves one capacitor and one resistor in series, and you take the output across the resistor. When you do that, it can also be considered, as you might perhaps know, as a high pass filter, because you can see when the frequencies are very large, the reactance offered by the capacitor, which is inversely proportional to the frequency, will be very small, and therefore almost all the voltage will go through the capacitor. It will become almost like a short, and therefore what you get will be a full output. But when the frequency is very low, very close to DC, then the capacitance will be the reactance offered by the capacitance will be very large, and therefore very small amount of voltage only will be able to pass through, and therefore it passes high frequency component and it does not pass low frequency component close to the DC. So that is why this is called a high pass filter. High frequencies will be passed through this filter. Incidentally, this can also be called a differentiating circuit. That is reasonably simple to understand. I will try to explain to you how we can do that when we actually go to the circuit. So a very simple differentiator circuit I have shown here using an op amp, where again the same network which I discussed a moment ago is being used. You have a capacitor and a resistor. You know, in this circuit, this input is actually connected to ground, the non-inverting input, and therefore this becomes a virtual earth. The minus side, this point becomes a virtual earth, and therefore whatever voltage I apply is actually between this and this point, and that means it is only across a capacitor. And similarly here, if I measure the output voltage, I always measure the output voltage between this terminal and the ground, and now because this point is equivalent, being a virtual earth to ground, what I actually measure is the voltage between the output terminal and this point, which is nothing but the voltage drop across the resistor, which is what I am going to measure as an output voltage, and the input voltage is applied across the capacitor. So what is the consequence of that? The consequence of that we can understand. For example, if I assume an input signal, a sine wave, y is equal to a sine omega t, where a is the amplitude and omega is the angular frequency. So a sine omega t is a standard sinusoidal voltage that we have. If I differentiate this, dy by dt, you know, will become omega a cos omega t. Sine will become cos on differentiation, and this omega a is a new amplitude of this cosine function, and therefore I call it by a new variable indication a prime. So a prime cos omega t is now the differential of the input voltage. Dy by dt is a prime cos omega t, which can also be written as a prime sine omega t plus pi by 2, where a phase factor is introduced. Because of the cos, sine has become cos, so that means it has to have a 90-degree phase. Therefore I rewrite this equation as dy by dt is equal to a prime sine omega t plus pi by 2. So this, if you compare with the y is equal to a sine omega t, that is input signal, you can see they are of the same type. This also a sine wave, this also a sine wave, except for a phase factor, and the a has now become a prime, the amplitude has become a prime. But it has got some very specific consequence, and that is this a prime, you might recall, is nothing but omega multiplied by a, where omega is a angular frequency 2 pi f. Omega is angular frequency and it is equivalent to the 2 pi f, where f is the frequency of the input. So omega, the amplitude is going to be a function of frequency. Now this has got some very important consequence. What is that? The value of a prime is no more going to be a constant. If I send larger frequencies, high frequencies, 100 kilohertz, 200 kilohertz sine wave, you would find the amplitude for that wave will be very large. If I send smaller frequencies, 100 hertz, etc., the amplitude a prime can be very, very small. So therefore what is going to happen if I have a specific signal, maybe a square wave or something, even a sine wave, you know always there will be some noise voltages which will be coming into the game at the input. Along with the signal, there will be some noise added to that due to say extraneous reasons, and these noise can have different frequencies. We have no control over them, and therefore the spectrum of the noise can involve very high frequencies as well as low frequencies. Now what is going to happen if the frequency is higher, that is preferentially amplified by my differentiation circuit, and therefore the output you would find more of the noise signal will be amplified than the signal, and ultimately it may happen that the entire signal will be completely buried in the noise, and therefore when you use a differentiation circuit you have to be very, very careful with reference to noise signal. Now how we are going to avoid this I will explain to you in a moment. Before that I wanted to tell you the output voltage is going to be minus I times R, which is very simple to understand, because you can see that whatever is the current that is going to flow in at the, as soon as you apply the V in, this current almost all of them will flow through R, because very small current only flows through the op amp. This we have seen any number of times earlier, and therefore the input bias current of this amplifier is going to be very, very small. I will explain in more detail about what the input bias current is all about later on, but you can for the moment imagine that the current actually passing through the amplifier is going to be very, very small because of the large input impedance associated with the amplifier, and therefore almost all the current which is flowing due to the AC signal applied through the capacitor will only travel through R, the feedback resistor, and therefore V output is nothing but I into R, where I is the current flowing through the R, and this voltage is going to be negative because the current is flowing towards the output from the ground, and therefore this voltage is going to be negative, and that is why I say the output voltage is V output is equal to minus I into R, where I is the current flowing through the resistor. Now we also know from fundamentals I is the rate of flow of charges, I is equal to dq by dt, the rate of charge flowing, and that is equal to d by dt of Cv, because the q is associated with the capacitor at the input, and the q, the relationship between q and the capacitance is q is equal to Cv, therefore differential of Cv divided by dt. In this C is a constant, V is the only thing which is the input voltage which is going to vary, and therefore I can take the C out, therefore this equation I becomes C into dV in by dt, right. This is the current. Now we combine it with the output voltage, so the V output will now therefore will become I into R, that is minus RC or CR into dV in by dt. So this shows very clearly that the output voltage is the time derivative of the input voltage multiplied by a constant which comes into the game because of the value of the capacitance and the resistance that I have used in the circuit. If I choose R is equal to 1 megohm for example, and C is equal to 1 microfarad, the product RC will cancel out, it become 1, and therefore RC becomes 1 second. RC is a time constant, we normally measure it in seconds, so RC will be 1, and the V output will become minus dV by dt. So this becomes a simple differentiating circuit. Right. Now I will explain to you about the circuit. So here this is the basic circuit which involves one capacitance and one resistor, but that is slightly modified here for a very specific range of frequencies in the range of 1 kilohertz. And so you find I have used a capacitor whose value is 0.01 microfarad and a feedback resistor which is 10K, and I have also used a resistor here which is a very small one, 270 ohms. So I have used 270 ohms in addition in series with a capacitor, then there is a 10K resistor in the feedback, and I have also used a 10K resistor for the other signal for connecting to ground. This 10K I have added for balancing the input bias current differences between the two input, about which I will discuss little more in detail later on. So what I am now going to do is, this is my differentiating circuit. Why I have added this 270 ohms at the input is because precisely the reason that I already mentioned to you in a differentiating circuit, the output gain is going to be a function of frequency. Therefore higher frequency components from so many other noise sources can be preferentially amplified, and therefore the output will become buried in noise. To avoid that, I introduce a 270 ohms, so that whatever noise that is generated at the input side will be dropped across the 270 ohms. The 270 ohms will make sure that not much voltage passes beyond this point, and therefore you would find the noise currents due to the noise will be very small, and therefore they will have very little effect at the output, whereas because it is a value is too small, 270 ohms, it will not greatly affect the input signal, which will be in the order of volts. So if I apply, then I will get that. Okay, how do I check whether it is performing a differentiating operation? If I give a sine wave, I have no way of knowing it, because a sine wave after differentiating becomes another sine wave or cosine wave with a with a phase difference of pi by 2. Therefore I would not be able to distinguish between the input and output with any characteristic features, and therefore I would rather go in for the well known fact that we have already learned in the integrating circuit, that when I apply a square wave to an integrating circuit, I get a triangular wave. We all know differentiation is the inverse of integration. Therefore if I apply, what will happen if I apply a triangular wave at the input? I am sure you would immediately recognize that I must get a square wave. For an integrator, if I apply a square wave, I get a triangular wave. So, for a differentiator, if I give this triangular wave, I should get a square wave, as simple as that. So, we would try by applying a triangular wave at the input, and we will try to see whether we get a square wave. So, I have shown you here a picture. In the first one, you see the input is a triangular wave and the output is indeed a square wave. Now, the differentiation of a ramp is constant multiplied by time. Okay, this is a time axis, this is a voltage axis. If the voltage is continuously increasing with reference to time, that means it should be c time. There is a finite slope associated with the straight line, therefore it is a constant multiplied by time, and differentiating it should become a constant. That is why it is a constant here. And when it comes down, again a ramp, then it has to be again a constant with reference to the negative side, therefore it is a constant here. So, you can see the square wave is formed from the triangular wave. We will also see it in the actual demonstration. We also I wanted to just indicate to you what will happen if I give a square wave. If I give a square wave as the input, what will happen? You know what is the differentiation of a constant? The differentiation of a constant is 0, and therefore you get a 0 volts here in the output. But what is the differentiation of a vertical line? The differentiation in the Vt curve is nothing but the slope of the line, and the slope of this line is actually minus infinity, going down to infinity, and therefore I get a straight line going up to minus infinity. But due to actual practical limitations, you do not get this line going all up to the infinity, but it is having a finite length. Now, then you have again a constant voltage here on the negative side, and that again should become 0, and here it is a positive going pulse towards infinity. That is why I am getting here. And so, you can see the square wave when I apply at the input of a differentiating circuit, I should get series of sharp pulses at the transition point, and I should get 0 volts whenever the voltage is constant, plus V or minus V, etc. So, these two will be the two different waveforms that I wanted to just explain to you how the differentiating circuit is reacting. Now, the gain, which is a function of frequency j omega, is equal to V out by V in, and the V out is across the R feedback resistor and V in across ZC, therefore it is minus j omega RC, because ZC is 1 by j omega minus 1 by j omega R, j omega C, therefore it becomes minus j omega C RC. So, the V output is minus j omega C RC into V in from this equation, and that is equal to minus RC dV in by dt, because minus j omega V in is nothing but the differentiation of the input signal dV in by dt. Right. So, the dV by dt is nothing but I by C, current divided by the C. Here at the input side, the differential voltage is V in minus 0, this is 0 here, this is V in by dt is equal to 1 by C 0 minus V out by R at the output, and that is also the same as what we have already seen. Right. So, if you look at the frequency response curve, you would find it will be something like this. It is because it is a superposition of two curves. One is due to the op amp, about which I have not yet discussed, but I will discuss at some detail later on. You have a constant gain up to some frequency, and then it rolls off with a constant slope at the end due to the internal capacitance and things like that, and therefore this is the bandwidth graph corresponding to, or the board plot corresponding to the op amp, and this is the response of the RC circuit that I have, and therefore both of them will give me a resultant which is actually shown by the solid curve here. Right. Therefore, basically we also saw that it is going to be a high pass filter, and that is what also is seen from the frequency response curve. Now, I will quickly show you a demonstration of the circuit, a simulation of the circuit. Here on this screen I have a breadboard, I have the dual supply, I have the function generator which generates square wave in this case, and I have an oscilloscope on this side. Now, I make auto setup, that means op amp goes in and the various components will go and occupy the appropriate places predefined, and all the wiring is being done with reference to the power supply, the input voltage or the function generator and the oscilloscope, etc. So, for reference I have also shown you the actual circuit on the bottom screen here. So, you have 270 ohms in series with a capacitor which is a 0.01 microfarad, and you have a 10k resistor which is connected to ground at the pin number 3, which is the non-inverting input, and you also have a 10k resistor which is at the feedback between the 2 and 6 terminals of the op amp. So, it is exactly the same as what you have here, and that has been wired. Now, I will switch on the power supply, I switch on the function generator, and I also switch on the oscilloscope. If I now apply some 500 hertz or so and about 1 volt, you can immediately see that a triangular wave given as the input, this is actually a triangular wave function generator, produces a square wave, and you can also see the amplitude is multiplied by 2 because of the values that I have used here in the specific circuit. So, a triangular wave given to a differentiating circuit should result in a square wave at the output. That is what I wanted to show it to you. Now, we will also try and do a actual demo of the circuit. I will show you the demo now. Here I have the differentiation amplifier differentiating circuit. It is exactly the same as what I discussed already. You have the 741s here, and you have the 0.1 microfarad and 270 ohms, and the 10k in the feedback, and there is another 10k at the non-inverting input connected to the ground. You have a input which is actually obtained from this function generator, which can be varied in frequency. You have a sine, square, triangular wave, etc. All those outputs are there. These knobs are for applying different frequencies. I have right now applied 1 kilohertz. I have pressed this button, this corresponds to 1 kilohertz. So, it is about 1 kilohertz, and this measures approximately the amplitude, which is about 200 millivolts. So, this is the input to this circuit, which is also wired here. You have the same op amp, and the wiring is exactly similar to what I show in the simulation also. Now, this is a dual supply, and the plus minus voltages are applied along the rail sockets, and then the output is monitored. Both the input and the output is monitored in the oscilloscope, and you can see that I have got a triangular wave at the top, which is actually the input, and what you see at the bottom is a square wave, which is the differentiated output. Now, if I change the frequency, you can see the output is also changing correspondingly. There is a phase factor which you are not able to exactly see, but you can see the triangular wave becomes a square wave when I apply through from a function generator. I also mentioned to you what would happen if I apply a square wave at the input of the amplifier. Therefore, I now change the input to a square wave, and you can immediately see the two sharp pulses corresponding to the transitions high to low and low to high. You see that, and that is corresponding to the differentiation of the square wave. So, this is the output waveform with sharp spikes corresponding to these transitions from high to low, and the square wave therefore will give me a very sharp pulses. If I put a diode, correspondingly I can get rid of either the bottom pulses or the top pulses, and I can use it for triggering other circuits. Now, you can also see that as I change the frequency, the output also changes. If I reduce the signal amplitude, the output will also show slight variations on that. If I give a sine wave, you find both of them are sine wave, because one is a sine wave, the other is actually a cosine wave. Therefore, there is only a difference of about 90-degree phase, which cannot be very precisely seen here, but you can certainly see that there is a phase difference. If you look at the corresponding peak positions, you find they are not in the same vertical line. There is a relative shift, and that corresponds to the cosine wave. The bottom one is a cosine wave, the top one is a sine wave. I will again come back to the square wave, and you can see the spikes. So, this circuit performs what is known as a differentiation of the input signal with reference to time. Right. Now we have seen the demonstration as well as a simulation of the differentiating circuit. We can also have several variations of the differentiating circuit. For example, I can have multiple signals. In this circuit I have used a summing amplifier, but I have used 2 capacitors on the 2 input side, and therefore it becomes both the output will be the differential of the 2 input signals. So it is a sum of 2 terms, each of the term will correspond to the differentiation of the V1 signal and the V2 signal, and that is what I will get. You will have the summing as well as differentiation performed on the signal. Similarly, I can also have another differentiating circuit where I have used both the input terminals, the non-inverting terminal and the inverting terminal, both of them are used here. So this is another variation of the differentiating circuit which also can be used depending upon the requirement. When you want to apply to different applications, you can try to use these type of circuits. Now with this we have completed most of the mathematical operations that I wanted to discuss. Now I will not stop here, because I should justify why these mathematical operations are important, how they are going to be useful in different applications. Now I already mentioned to you that these operational amplifiers are very useful in analog computation. When you want to perform analog computation, that is on analog signals, when you want to apply some mathematical equations, I also mentioned to you most of the physical phenomena can be represented by way of a differential equation. So if you are able to have a differential equation and solve the differential equation, you would have reasonably solved and understood the basic phenomena you wanted to understand. Of course, for corresponding to the boundary conditions which you have to apply corresponding to the difference amplifier differential equation. So it becomes convenient for us to provide an electrical analog of the actual physical phenomena by constructing certain operational amplifier circuits with which I can perform the solution of the differential amplifier. I can obtain the solution of the differential equation instead of mathematically or instead of actually working with a real system. I can take an analogous system in which the variables are simply voltages, currents and things like that, and I can perform the differentiation, or the differential equation can be implemented electrically and solve the differential equation. Thereby I would have solved the actual real time problems that I used to handle. So these mathematical operations that we discussed are useful in such applications. As an illustration, I want to just give you 2 different types of application. One is solving simultaneous equations, and second one is solving a differential equation. Let me take up the first part, which is solving simultaneous equation. What do you mean by the simultaneous equation? If I have 2 equations as I have shown on the screen, for example, a1x plus b1y is equal to c1 is one equation, a2x plus b2y is equal to c2 is another equation. So I have 2 equations. From this I should solve obtain. What do you mean by solving these 2 equations simultaneously? Means I must obtain a value of x and y which will satisfy both these equations. That is what I mean by solving the simultaneous equation. That means the x and y, whatever value I assign, that will be satisfied by both these equations, where the a1, b1, c1, a2, b2, c2 are coefficients, the constants, numbers. So this mathematical operation of solving the simultaneous equation, most of you know, you would have studied in your school, and this can be done also electronically using operational amplifier, and the solutions will be in forms of voltages. So that is what I am going to now attempt to explain to you. So if I take the first equation, a1x plus b1y is equal to c1, I can rewrite this as, by retaining the first term, x is equal to C1 by A1, I divide throughout by A1 here. So, C1 by A1 minus B1 by A1 y when I take the y coefficient to the other side. So, x equal to minus C1 by A1 minus B1 by A1 times y. Similarly, the second equation can be solved for the y, and y is equal to C2 by B2 minus A2 by B2 times x. So, these two equations were derived from the first two equations, obtaining x from the first equation and writing the expression for y from the second equation. Once you have this, then you understand that this involves multiplication of a constant and either summing or difference. X is some quantity, some value C1 by A1 minus another value B1 by A1 multiplied by another variable y. So, this is completely amenable to all the techniques that we already discussed, basically the summing amplifier and multiplication by a constant. So, I can use those circuits and obtain these two equations independently. That is precisely what I have done here. In the next picture you can see this is the op amp. What I have done is I have taken B1 time by A1 times y. I assume B1 by A1 times y is available at this input. At this input from a voltage source I obtain minus C1 by A1 times this voltage Vs. This I apply. This feedback resistor is R, this also is R, this also, therefore this summing amplifier has got a coefficient of 1, R by R in both, but there is I am applying it to the inverting input, and therefore I am going to get all of them with a minus sign at the output. So, if I give minus C1 by A1 times some voltage into 1 volt, for example Vs is 1 volt, this I will adjust the potentiometer here such that I get minus C1 by A1 voltage. If I get that, you would find when it comes here it will become plus C1 by A1 because the gain factor in this is 1 R by R, and therefore I will just get the first term x equal to C1 by A1, but there is also another additional input, additional term, and that to obtain that I have used B1 times B1 divided by A1 times y, the other variable. If I apply it here, that will come at the output as minus B1 by A1 times y, and therefore I get here minus B1 by A1 times y. So, this is what we got from the first equation, x equal to C1 by A1 minus B1 by A1 times y, and that is precisely what I have implemented using this circuit with one op amp. Now, what I do the same thing with reference to the second equation, y is equal to C2 by B2 minus A2 by B2 times x. So, in this case you find exactly similar to the earlier one. I apply A2 by B2 times x at this input, and I apply C2 by B2 as a proportional voltage at this point, and these two will be added at the output with a negative sign because there is an inverting input here, and therefore y becomes C2 by B2 minus A2 by B2 times x minus A2 by B2 times x. This is what I get, and this is precisely what I have here in this equation. So, now what I do, there is x here, there is y here. So, this y I connect here and this x I connect here, therefore I cross couple these two outputs, and that means this amplifier will have the input from the other circuit, and that second amplifier will have the input from the first amplifier. So, thereby it becomes consistent, and now once everything is settled I will just go and measure the voltage here, that will give me the value of x, and if I measure the voltage at the output of the second amplifier, I will get the solution in terms of y. So, this is what I mean. So, that is the complete circuit that I have shown here. That is, I have combined the two equations. First I solve the first equation by using this circuit, solve the second equation by using this circuit, and then interconnect the x and y as I have shown here. This x I take A2 by B2, some fraction of that x, and apply at this input, and the y output comes here, I take a fraction of that and give at the input here, and therefore this becomes consistent. And if I measure the voltage here, it will be the value of x. If I measure the voltage here, that will be value of y corresponding to the simultaneous equation solution. Right. Having said that, it will be good to take a very typical example and see whether we can solve it simultaneously. Now I have taken a simple numerical example. X plus 4y is equal to 10 is the first equation. I previously discussed only with a1, b1, etc. some coefficient. Now I am taking actually real numbers. So x plus 4y is equal to 10 minus 3x plus 2y is equal to 12 are the two equations which have to be solved, and the solution x and y which will satisfy both these equations simultaneously will have to be identified. For that, as usual, I write what is x from the first equation. X is 10 minus 4y. So that is what I am writing here, x equal to 10 plus minus 4y, then minus 4y I put in a bracket. Therefore this is the first equation, and similarly from the second equation I obtain the y is equal to, this will become 12 by 2, that is 6, and this minus will become plus 3 by 2. So y is equal to 6 plus 3 by 2 x is the second equation. So having obtained the x from the first equation and the y in terms of x from the second equation, I can use an op amp to implement this in the summing mode and implement this in the summing mode and then cross connect x and y. That is all I should do. Now let us see whether we have done that. So you can see here I have chosen some values of resistors and I have complete circuit here in front of us. It is very similar to what I already mentioned to you. For example, I have used the Vs, the reference voltage, to be minus 5 volts, and I have used a 2K resistor here, 4K resistor here in this first amplifier. So if I have only this input, what is the gain of this? The gain of this is 4 kilo ohms divided by 2 kilo ohm with a negative sign because I am applying to inverting input. So minus 4 by 2, that is minus 2 is the gain, and that should be multiplying the input which is minus 5 volts. So it will become plus 10 volts at the output if I have only this first signal. Therefore I have the plus 10 at the output corresponding this, and when I apply the y here, this is 4K and this is 1K, so the ratio is 4 times y is what I get, but because I am applying to the inverting input, I should get minus 4y at the output due to this input. So I have a minus 4y. So my x is, which is the output of this amplifier, is the combination of two terms. One term is corresponding to 10 volts, the other is corresponding to minus 4y, y is the output voltage coming from somewhere else, and this is the first equation. So this op amp that you see here is corresponding to the first equation. Corresponding to the second equation, you can see I have in the next op amp, you have 1.5 kilo ohms and 1 kilo ohm, and so the ratio is 3 by 2 times x, that x is connected here. So 3 by 2 x with a negative sign here, I will get minus 3 by 2 x here, and this is 470 ohms which is close to 500 ohms, and this is 1.5, therefore it is 3 times, therefore 3 times the input voltage plus 2, that will give me 6 volts, again with a minus, therefore it is minus 6 volts. So what I get will be a minus y. Minus y is what I get here because it is minus 6 volts minus 3 by 2 x from this amplifier, and so I get a minus y. But here I have to apply y plus y, and therefore I have introduced one more op amp here in which I have just used simple inversion, 10K here, 10K here, and I give the minus y, and therefore the output will become plus y with a gain 1 because 10 by 10 is equal to 1. So this becomes plus y, and that y I bring an interconnect at this point. Thereby you find I have consistently connected the whole circuit, and therefore if I measure with a multimeter what is the voltage here, and if I measure the voltage at this point or at this point, I will get the value of y, and at this point I will get the value of x. So the equation has been solved successfully using electronically. That means by using 3 op amps, one op amp for one circuit, another op amp for the other circuit, and the third op amp is for performing a simple inversion. So I have used all the mathematical operations corresponding to multiplication by a constant, summing amplifier, difference amplifier, and all these things put together will get me the solution of a simultaneous equation. So what will be the value of x and y? if we wire the circuit and measure, you will get the solution. But before we do that, let us also try to do that by the normal analytical method. X plus 4y is equal to 10 minus 3x plus 2y is equal to 12 are the two starting equations. So multiply 1 by 3, so it becomes first one 3x plus 12y is equal to 30, and this is minus 3x plus 2y is equal to 12. If I add them together, I get 14y is equal to 42 and y is equal to 3. So y is equal to 3 is the first solution, and I use that in the next equation. X plus 4y is equal to 10, x plus 4 into 3 12 is equal to 10, therefore x equal to minus 2 is the second. So the solution, if I do analytically, I get x equal to minus 2 and y is equal to 3. So if I wire this circuit, which I have already shown to you, and measure the voltage here, it should be minus 2 volts and the voltage here should be 3 volts, because x equal to minus 2 and y is equal to 3 are the solutions of the simultaneous equation. So having seen that, let me go and show you a demonstration of this simultaneous equation. I have actually taken the same equation, same two equations, and we have wired the same circuit which I have shown here, and then we have tried to measure the two voltages. So let me show you the actual demo. So here you can see the same circuit is shown, the same circuit. There is a minus 5 volts here, the 2k resistor, 4k resistor, and the y is coming all the way from the output for the third amplifier, and this is the first amplifier which gives me the value of x, and this is the second amplifier which has got 470 ohms with a plus 2 volts and 1 kilo ohm and 1.5 kilo ohm as a feedback resistor, and this is the inverter with a 10k resistor here and the 10k resistor here, so that the minus y becomes plus y, and thus plus y is again fed back to this circuit, so that once I wire the circuit with all these values, if I measure the voltage here, that will give me the value of x, and if I measure the voltage at this point, I will get the voltage y corresponding to the solution x and y of this equation. So this is the actual circuit wired with the 3 op amp as seen here. So this is the first op amp that you have here, you have got the 1k and the 2k and the feedback resistor, all those things, and this is the second op amp here, and you have got the 470 ohms and the 1k and the feedback resistor 1.5k, and the last one is 10k with the feedback resistor 10k is an inverter, and the output of that is all the way brought and given at the input corresponding to y. So this is precisely the same circuit which I have wired, and I wanted to measure the voltage here. So now what I do, I use this multimeter and connect it to measure the value of y, x, and this multimeter I use to measure the value of y. So what is the value of x? I do not know whether you are able to see that. It is actually minus 2.264. It should be minus 2, you are getting minus 2.2 or something, and the value of y is plus 3, and that is what you read here, 3 volts, and x is minus 2.268. There is a slight variation here, it should be precisely minus 2 volts, it is not, because I have not used very precise resistors here. For example, I have used 470 ohms instead of 500 ohms, and all these resistors will have some small variation because of the tolerance, and therefore there is some residual extra voltage that comes in terms of here 2.2. If I use very precise values of resistors at every point and measure, I will get very precise value of minus 2 volts. I do not know whether you are able to see the minus sign here, it is minus 2.2 volts, right. This is minus 2.2 volts, that gives the solution with reference to x, and this multimeter gives the value of y, and this is what we have actually done as an application of the operational amplifier mathematical operations. So I have actually shown you a real circuit which is being implemented using these two equations, and we found that the value of x and y will be corresponding to the voltages will be appearing when I measure the x voltage and the y voltage, that will correspondingly give me the solution of the equation. So it is more for an interest that I have shown you this circuit, but it is not for such simple applications that we use operational amplifier. It can be used for much more complicated physical phenomena which can be represented by a differential equation or something like that. You can on your own try other simultaneous equation you can write and then try to formulate your own circuit, design a circuit which will correspondingly solve that particular simultaneous equation, and it is much simpler. Quickly you can wire it and you get the solution. Now what will happen if I go for a 3 variable simultaneous equation, not only x and y but x, y, z. You can almost in a similar fashion solve. That means instead of having 2 amplifiers you perhaps will have to have 3 amplifiers corresponding to x, y and z, and then provide the necessary feedback. You can write from the first equation what is x equal to in terms of y and z. From the second equation you can write what is y is equal to in terms of z and x, and the third equation you can obtain z is equal to in terms of x, y and a constant term, and then implement a 3 input summing amplifier where the corresponding terms will come at the input and you get the x and the y and the z. So 3 amplifiers I will do, and then I will interconnect the x to x and y to y and things like that. Thereby you would find you can in principle solve even a 3 variable simultaneous equation. So the 3 variable simultaneous equation will be slightly more involved than a 2 variable simultaneous equation. So if I give an example of a 2 variable simultaneous equation to be solved electrically, you may laugh at me that it can be very quickly done by an adept mathematician in a very short time, whereas if you go to a 3 variable simultaneous equation it involves much more involved calculations, and therefore it might perhaps be simpler if I can just wire a simple circuit and provide appropriate input voltages and things like that. I will be able to perhaps solve faster. So analog computers in actual reality, now there are not many of them available in these days because most of the analog computations can now be done much more efficiently at higher speeds by using digital computers, and therefore not many applications are now being implemented using analog computer, but still because of the advent of operational amplifiers, the analog computers, the various mathematical operations have become very handy and useful in several different types of applications that we come across. Beyond the basic electrical engineers, there are plenty of other engineers from other branches and scientists who are also making use of these type of circuits for different application purposes. I only showed you a simple example of a simultaneous equation, but we can also go further and discuss about the solution of some of the differential equation. I wanted to just give a couple of examples. So on the screen you see there is a differential equation which is a very well known differential equation corresponding to the radioactive decay law. So dN by dt is equal to minus lambda n, I am sure is a very familiar equation to most of you, where the n is the number of nuclei that is undergoing decay, and the rate of decay dN by dt, the number of nucleus that is undergoing decay is shown from per time is dN by dt, that will be proportional to the number of nuclei available at the first instance. So this is written in the form of a simple equation dN by dt is equal to minus lambda n, where lambda is a decay constant, a proportionality factor which comes into the game, minus lambda n. Now if I want to solve this, what is that I should do? I will actually use a very simple integrating circuit and apply dN by dt as the input voltage, whatever is that, and what I get will be a corresponding lambda n. So that is what is shown here. So, I have an integrating circuit here. So, I connect the rate dN by dt here, and then after integration it becomes minus n with a proportionally constant, which comes about because of the RC time constant. We have already seen that, the product of RC, as well as some initial voltage on the capacitor, which can be adjusted using a R reference, E reference, using this R1 R2 potential divider. Therefore, I can apply this, and thereby I will get minus, if I use a potentiometer and take some minus lambda times the output voltage, minus lambda n, and apply it to the input here. So, you find the equation becomes satisfied, minus lambda n given at the output, and that will be what you get out of the differentiator. And so, dN by dt is equal to lambda n is implemented here in a very simple fashion using one single op amp. You can also complicate the scheme by having the multiple decay. So, first it goes Na decays to become Nb, and Nb decays again to go into Nc and things like that. So, the equation becomes much more complicated. You have to make use of the presence of Na also here in the second equation, and Nb, and in the third equation Nb and Nc. So, the mother, the daughter, and things like that. So, you have more number of variables here, and this also can be implemented by using a similar operational amplifier circuit. Now, we can also discuss differential equations of a more complicated manner. Some of you may be familiar with the equation that I have written here, the second order differential equation, m d square x by dt square plus b into dx by dt plus kx is equal to 0. If I do not have this term, it becomes a simple harmonic function, differential equation corresponding to an oscillator. So, m d square x by dt square is equal to minus kx is corresponding to a vibrating system. Now, this b dx by dt, which is corresponding to a velocity term dx by dt, will provide some damping with reference to the vibrating system, and therefore, this is for a damped harmonic oscillator, a simple harmonic oscillator, and therefore, this equation can be solved by simply rearranging dx square by dt square is minus b by m dx by dt minus k by m x. So, I rewrite and then I implement using the op amp integrators. Integrators are much simpler to work with than differentiator. I already mentioned to you, you may get into problems of noise when you introduce a differentiator. Therefore, it is always preferred to use the integrator. So, you use a integrator, assume that d square x by dt square is available at the input, then you can integrate it to get dx by dt at the output. You again integrate it using this circuit and you get an x. Then you provide the corresponding k by m x proportionality here, and here what you have done is the dx by dt is multiplied by a proportionality constant minus b by m using this potentiometer, and so that output is just inverted because this is minus here, this will become plus, and these two terms is now added, that is what is d square x by dt square. So, that is given at the input here. So, you find this becomes a consistent circuit with the input and the output conforming to each other, and therefore, you get the complete circuit, differential circuit implemented using this op amps, integrators mostly, and one inverter. Two inverters are, this is a summing amplifier, this is an inverter, these two are integrators. The initial condition can be set by using E reference and things like that, and the greatest advantage of this is that you can understand a real situation if you know what is the corresponding damping factor, the frequency factor, and things like that. You can modify this and try to implement the corresponding system over here and study that very quickly. When I do a solution, you find the solution mathematically, analytically. If I do, I will get the solution after performing certain mathematical manipulations, and if I want to change some of the variables or the coefficients, then I have to almost start all over again and solve the problem solution, obtain the solution once more. Here, all that I have to do is modify some of the voltages or the coefficients b by m or k by m factors, which are basically by using potential dividers. I can quickly change them for a new equation and then implement that in a moment's notice, and then try to understand how the stability of the oscillator is, what is the damping that ultimately leads to, and things like that. So you can try to understand the vibrating system in a very simple way, and by introducing several different modifications very quickly, and that is one of the greatest advantages of using an analog computer in place of an actual model, physical model that you want to study. You can make an analogous electrical circuit and understand the behavior of the electrical circuit by changing the different parameters, and that way you will get better insight into the actual working principle of the physical phenomena that you want to understand. So what we have today seen is how differentiation can be performed using an op-amp, and as an application I have taken two simple applications. One is solving a simultaneous equation using operational amplifier, and I also discussed how this can be used for solving more complicated differential equations by using simple integrators, summing amplifiers and inverters and things of that sort, and how a physical phenomena can be understood in real situations by using analog computation. Thank you very much.